Okay, thank you. Thanks a lot. And I'd like to thank also Fernando for inviting me to come. It's always a pleasure to come here. And well, this is a joint work with Leonor Ferrer and Paco Martin from Granada and Ray Matseo from Stanford. Okay. I'm going to work with minimal surfaces in H2xR. And the model I'm using for H2 is going to be the unit disk, the Poincaré disk model. From time to time, I'll use also polar coordinates, okay, in these disks. And also, I'm considering the product compactification of the manifold. This is the solid cylinder. Okay, so the Plateau problem at infinity for me in this talk is going to be take some Jordan curves in this cylinder at infinity, and we wonder if there exists or not minimal surfaces whose boundary, ideal boundary, is these Jordan curves. Okay, I mentioned that. Okay, for me, I look for connect surfaces also. I mentioned that because also Baris Koskounuser has some results about the Plateau problem at infinity, but for him, he looks for area minimizing surfaces and not necessarily connected. So there are different approaches for this kind of problems. Okay. Well, the first example we can think of is consider just in the solid cylinder. Okay. Some curve projecting graphically onto the ideal boundary of H2. Okay, and we want to know if there exists some minimal surface with this boundary at infinity. And this was solved by Nelly and Rosenberg some years ago. And the idea to prove that is natural. So take a sequence of cylinders converging to the whole space, project your Jordan curve onto these cylinders, and we know that there exists the solution of this Plateau problem. And since we can use the maximum principle with translated copies of the surface, we prove that it has to be a graph and is unique. Okay, there's only one solution. So now take the different graphs whose boundaries are in these cylinders converging to the whole space, and these graphs are bounded because they are containing some horizontal slabs, so there exists a limit. Okay, and it remains just to prove that the ideal boundary is the right one. And what you can do there is okay. Pick your favorite point there, and well, we have the value of the Jordan curve there, which is a graph, and since we are assuming is continuous, there's some neighborhood of that point at the infinity boundary, such that this the values of the functions there is at a distance less than epsilon from your height. Okay. Now consider a geodesic joining the endpoints of this neighborhood, and consider the graph defined on this domain whose boundary values are plus infinity on the geodesic, and this value plus epsilon on the arc at infinity. Okay, it exists, this graph, and we know is invariant by hyperbolic translation along this geodesic. So in particular, is foliated by horizontal curves, which are equidistant curves to the geodesic. Okay. So again, using the maximum principle, this is a barrier from above for each one of the graph in the sequence. Okay. So let's say that since it's invariant by hyperbolic translation, I'm just drawing a section there. So it's going to infinity there, and at infinity takes this value. Okay, And what we know is that all the graphs remain below this boundary, okay? This barrier, sorry. And we could do the same, taking minus infinity there and minus epsilon there. So we have another barrier below. And we know all the graphs are between these two barriers, okay? And when epsilon is going to 0, we have the same value here, minus epsilon. When epsilon is going to 0, there's no room for the graph to escape. So the asymptotic value has to be the right one, okay? And we can do that all over the neighborhood of the end. So at the end, we know that the asymptotic values are the prescribed ones, okay? Well, this is well known. And also quite recently, Kleckner and Mazzeo proved that if you have a graph, a vertical graph, not necessarily entire, as in this case, but just near some part at infinity, the extension is as good as the boundary values at infinity. In this case, we were assuming that the values were continuous, so the surface extends continuously to the boundary. In the case you assume the function is 2 alpha or ck, C2 alpha or ck or something, the extension is going to be as C2 alpha, ck or whatever. Okay, so in other words, what we have is a boundary is a surface with boundary in the compactification. Well, so the problem we consider was, instead of considering one of these Jordan curves, we consider two of them, okay? And this is the problem we state. So we were looking for properly embedded connect minimal surfaces whose boundary are this kind of Jordan curves, which are graphical at the end. To simplify things, or starting with, we consider annuli. Okay, we prescribe this topology. And since we want to have something embedded, we assume that the curves are one below the other. Okay. And the motivation of that, the prototype we have are the catenoids. Okay. We have in this space a rotational invariant catenoid found by Nelly and Rosenberg. And if you have two horizontal circles, we know that it exists a catenoid. Okay, as far as the distance between the circles are at distance less than pi. What is happening when the distance is going to pi is that the necks are getting larger and larger until disappearing at infinity, horizontally speaking. Well, all these graphs are quite symmetric. They are also big graphs with respect to some plane in the middle. Okay? And they were characterized using the symmetries by Nelly, Saerp, and Tubiana, okay, as the only annuli with whose boundary are horizontal circles. Well. And trying to deal with this problem, it wasn't that simple as we thought at the beginning. We tried to look for some properties that they satisfy. An important one is that in the case one such annulus exists, a neighborhood of each one of the ends has to be a graph. Okay? We proved that by following the technique of Collin, Osbirth, and Rosenberg in the slab theorem. Okay, what they proved in our context is that in the case that the annulus is containing a horizontal slab of width at most pi, then the ends are graphical. Okay, in this setting we have. And where does this pi come from? Because what they need is to have a family, a continuous family of annuli to go all around the neighborhood of the end. Okay. And what they consider is a compact piece of the rotational catenoid and translations of this catenoid. So at the end, okay, so this is why they need that each one of the end is in a slab of with pi. But we don't have that in our case. So in order to adapt their proof, what we need is to look for some continuous family of annuli, compact annuli, in such a way that when you move around the boundary of your annuli doesn't intersect your surface. So the idea to do that is more or less the same as here. So as I said, sorry?
The slides.
Ah, sorry. Oops, a lot. Sorry. Okay. Okay, I leave it. Okay, so what is happening, as I said before, since we are assuming that the boundary is a graph, we have these barriers as before, and they are invariant by hyperbolic translations. So we can cut with a width of with a slab of width, for instance, 4 epsilon, okay, and the intersection there are going to be equidistant curves to this geodesic. So what we get is the our surface over this domain here is contained in a slab very small, okay. So we are allowed to consider some compact piece of a catenoid not touching infinity, okay? Okay, this way. Sorry, it goes downstairs. In such a way that when you move this catenoid, you translate horizontally this catenoid over this domain, the boundary doesn't intersect your surface. Okay, but this is just in this domain. So we need to go around. So what we do is that by compactness, we can do that for some other points at infinity, infinitely many, in order to have the same thing. So in these different regions, you have you can translate horizontally your catenoid without intersecting the boundary your surface. And the idea is, well, you take this catenoid, you arrive to this intersection domain there, and here you can translate it vertically upstairs or downstairs in order to have the right height for this other next domain. And then here you are allowed to translate horizontally until arriving here, and you do the same. So considering vertical and horizontal translation, you can go with your compact annulus all around a neighborhood of DM. And then we can follow their ideas in order to prove that it's a graph. They use what they call the dragging lemma, inspiring ideas by called the Minikotsi. Okay, he's in that paper. Okay, so once we know it's a graph, we have an important property we are going to use, and but I also have bad news. Is that in general we don't have a solution. The simplest case we can think of is if the curves are very far apart one from the other, in such a way that you have a horizontal slab of width pi in the middle. You can use with the maximum principle of the family of catenoids. You get a contradiction, so you don't have a solution for the Plateau problem. But we have proved something more stronger, is that maybe you don't have this slab in the middle, but point by point, if the distance is bigger than pi, we prove you don't have a solution for the problem. How do we do that? Well, let's suppose it exists, and now we consider the Jordan curve as in the picture here, a piece of your Jordan curve upstairs, another downstairs, and joined by vertical segment at infinity. Okay, this is one of the curves considered by Koskun-Usser, and he's allowed to prove that there exists an area minimizing disk with this boundary. And the idea of the proof is quite simple. So it's as before, you consider a sequence of cylinders converging to the whole space. You project the boundary there, take the solution of the Plateau problem, which is area minimizing. And now the idea is taking limits. It doesn't escape to plus infinity or minus infinity because they are bounded, of course. But also we have barriers, horizontally speaking, because since the distance is bigger than pi, we have what is called the tall rectangles. You have two arcs, horizontal arcs, in such a way that the distance is bigger than pi there, and the vertical segment joining them. And we know that it exists a minimal disk bounded by this with this boundary at infinity, and is in fact is invariant by a hyperbolic translation. This was first obtained by Laurent Hosbirth when looking for all the examples whose horizontal sections have a constant geodesic curvature, and also by Saer Pantubiana when they were looking for minimal surfaces invariant by translation, horizontal translations. So we can use that as a barrier, horizontally speaking, because you can include one, at each point, below each point, you have the barriers in any direction, so your limit can't escape to infinity. Okay, so it exists that disk, which is area minimizing, and the idea now is we were picking this vertical segment arbitrarily. Okay, so now we start approaching them. On the other direction, and again we look for what is the limit. Okay, since we are assuming that it exists this annulus, we use that annulus as a barrier, so it's not going to disappear at infinity. Okay, so what we get is a minimal disk, area minimizing, in fact, whose boundary is your curve, your original curve upstairs, downstairs, and a segment at infinity, a vertical segment at infinity. This disk is not tangent to the cylinder at infinity along this vertical segment, because you can again use as barrier tall rectangles from each part of the on both sides of this vertical segment. Okay, so there's an angle there. That means that in the compactification is not an annulus, it's not differentiable there. Okay, and now again we're going to read the contradiction now. Is that okay? Take this area minimizing disk, and now consider hyperbolic translation from this point to the opposite one. Okay. What is happening at the boundary curves at infinity, upstairs, downstairs, is that they are flatter and flatter. They are very flat, and everything else is accumulating in the opposite side. Okay? So as a limit, what we are having is that everything else in the middle is going to accumulate to some vertical segment there. So as a limit, what we have is two tall rectangles sharing the vertical segments, and we proved that it can't be area minimizing. Since we get that as limit of area minimizing surfaces, this is the contradiction. Okay. Well, so this is not so bad, because what is saying is that we have to assume that they are not very far apart one from the other. The distance has to be less than pi. Okay. But the next result about the non-existent result was quite bad. Because that, okay, what we're proving here is that if you have two Jordan curves and they are tilted apart one from the other, okay, we can, as I said before, we know that neighborhood of the ends are vertical graphs. So if you intersect with some vertical plane here, you are leaving two graphs, one upstairs, one downstairs, on the right. Okay, so you can reflect in order to start the Alexandrov reflection principle. And since they are graphs, you know that it's in one side of your surface and so on. So you can start the process. And you get that this annulus, if it exists, has to be symmetric. But the boundary curves were not symmetric. So that's the contradiction. Okay? So and why it was that bad, this result, is because we have the catenoid. And you can deform a little bit one of the curves, and you don't have solutions. So it's because at the beginning we thought about using the catenoid to deform and being allowed to solve the Plateau problem in general. But it wasn't possible because of that. Okay. So the idea is trying to look for, extra hypotheses in order to have a solution. Okay, let's set the problem. So B is going to be the family of boundary curves, okay, the Jordan curves. And we assume they are C2 alpha in order to have good regularity to work. Okay, and we call A the family of all properly embedded minimal annulus whose boundary is in the set B. Okay. And now we consider the projection mapping its annulus to its asymptotic boundary at infinity. Okay, proving that the Plateau problem in general has a solution is equivalent to prove that this is surjective. But as I said before, there are some cases where you don't have a solution. So that was, we had to look for things, extra hypothesis to say that the projection is surjective. Okay. But okay, the idea was trying to use degree theory. Okay, B is Banach. Also, we studied the Jacobi functions of the annuli in the family A. We obtain expansions at infinity, allowing us to define charts for the family in A, the family of annuli A. So we got that this is Banach. Okay, so this is good. We had two Banach spaces, and we were able to prove also that this projection is Fredholm of index 0. The bad part is that it's not proper, so we can't apply the degree theory directly. And what is not proper? So take a catenoid and start translate it horizontally. Okay. The curves remain constant, so it exceeds the limit, obviously. Okay, but when you do that, the limit of your annuli is just two horizontal planes, and everything else is accumulating at infinity, disappears. So you're not, the limit is not in your family. So what we have to do is study the different sequences. The limit of sequences of annuli in your family whose boundary converge, and that's the compactness things, the compactness result we need. In order to do that, we distinguish different cases. As I said before, outside some cylinder, the intersection of your surface is just two graphs. Okay, so the different cases comes from how these cylinders are. The first simple case is that imagine you can take this cylinder uniform, okay? The radifix, the same cylinder for all the sequence. This is going to be good. We are going to have a limit there. Imagine you have a catenoid and the sequence is constant. That's the prototype, the silly prototype, okay? The second case is imagine that the radii is uniform, is exactly the same, but the cylinders are disappearing at infinity. This is what happened for translation of the catenoid. Okay, and this is going to be bad, as we'll see. This is the bad case. And the third one is imagine that these cylinders are larger and larger. I mean, you are not in the previous cases, so all the choices of cylinders are very big, okay, bigger and bigger, until I mean, the neck of the annuli explodes, horizontally speaking. Okay. One of the examples we can have in mind is take the family of catenoids. You start moving the boundaries, going apart one from the other until height pi. When you do that, the annuli disappear at infinity. And this is what is going to happen in general. Well, let's study the different cases. In case 1, as I said, this is going to be the good one. We are going to prove we have a good limit. Okay? So we have a fixed cylinder, and outside that, we have a sequence of graphs. And they are bounded, so it exists a limit. And as I said before, I mean, exactly the same idea. The boundary values are the right ones. Okay, so this is good. Outside the cylinder, you have a limit. So the problem, if there's a problem, is going to be inside the cylinder. Okay, let's take maybe a slightly bigger cylinder in order to assure that the boundary curves of this compact annuli intersecting with the cylinder converge. And what we are going to use is using a theorem by Brian White that said that the set of area blow-up and the area blow-up set satisfies in this setting the same maximum principle as minimal surfaces without boundary. Okay, so let's fix some height and take the family of catenoids, symmetry with respect to that height, and you start decreasing. I mean, the distance between the boundary curves, and the limit is going to be the horizontal plane. So what we obtain here is that none of these catenoids can intersect your set Z. So at the end, at that height, you have nothing. And you can do that for any height. So at the end, what you're proving is that the area blow-up set is empty. Okay? And now we use another theorem by Brian White, saying that in that case, where there's no bad points where the area is accumulating, going to infinity, you have a limit. This limit could have multiplicity bigger than 1. But in our case, we knew that outside the cylinder, the multiplicity was 1. So, I mean, we have a real limit. And we're done in this case. In the second case, so now you have a sequence of cylinders with the same fixed radii, but going to infinity. Okay? And what we are going to prove is that it happens exactly the same as for the catenoids. The limit is going to be the two entire graphs bounded by the Jordan curves that you have at infinity, joined by the vertical segment at infinity where everything is accumulating. Okay, and what is happening at infinity is that a catenoid, a real catenoid, is forming there. Okay, let's see the proof. So again, now you know that aside the cylinders, they are graphs, and the domains where they are graphs are bigger and bigger until these domains convert to the whole hyperbolic plane. Again, we know it exists a limit, and the boundary curves are the right ones. Okay, so it's by the uniqueness of the vertical graphs, they had to be the graphs spanned by your Jordan curve at the beginning. Okay, this is what we get. And now let's see how this catenoid is forming. What we do is at each step now, you translate in order that the axis of the cylinders are over some fixed point, let's say the origin. Okay. When doing that, what you have is some sequence in case 1. So now we know that it exists a limit. And as you are doing that, I mean, exactly the same as I explained before, the boundary curves are getting flatter and flatter and flatter. And in the limit, they are going to be at height constant, okay? And now we use that the only annuli bounded by constant, I mean, horizontal circles are catenoids. So a catenoid is forming there. This is the idea. Okay, finally, let's see what is happening in case 3. Okay, the prototype we have is, I mean, the catenoid whose height is going to pi. Okay, and what is going to happen is as for the catenoid. Okay, I didn't say that, but when the distance is going to pi, the neck are disappearing at infinity. But we can always translate in order to have some accumulation point. You can have even a fixed point over the origin, for instance. If you do that, what you get is this generalized catenoid, which is foliated by horocircles. Again, that was found by Laurent when looking for these all minimal surfaces whose horizontal curves had a constant geodesic curvature. And also by Benoit Daniel when looking for examples foliated by horocircles. Okay, and what is happening here is exactly the same. So if the cylinders had to be bigger and bigger, what we are saying is that there are points whose normal is horizontal accumulating to infinity. These are the points Pn. If you translate to have these points over the origin, what is forming there at infinity is this generalized catenoid. Okay, so it's exactly the same as for the family of catenoids. And the good thing for this case is okay, you have a limit which is not in your family of annuli. Okay, that could be bad, but the length we know that it exists. This example when the distance is exactly pi. So, I mean, if the limit of your Jordan curves convert to these two horizontal circles, you are escaping from your family of boundary curves. Okay, so it's not going to be the case. Well, now, as I said before, case 1 is good. We have convergence. Case 3 is good because it never happens in our case, okay, because the boundaries are too far apart one from the other. So we had to add some extra hypotheses to kill case 2. Okay, in the paper we have different things, but one of them, because I didn't have too much time, is I mean, what you want to avoid is the case of catenoids going to infinity. So you can take a finite group of isometries living invariant one fixed catenoid, and so that it doesn't live invariant translated copies of the catenoid. Okay, in other words, these hyperbolic translations are generating the decaying Jacobi fields. This is the Jacobi fields whose boundary at infinity is 0. Okay, they are vanishing as infinity, and they are essentially cosinus and sinus up to some factor depending on the radius. Okay, so for instance, we could consider the group generated by one translation. Okay, if you do that, I mean, the translated catenoids are not going to be anymore invariant by this group of isometries. Okay, so and this is going to be good. So well, this is the thing we had to consider, and now we restrict ourselves to everything invariant by this group of isometries. Okay, so now the boundary curves are invariant by this group of isometries. Again, the family of annuli, you impose that they are all of them invariant by this group of isometries, and you restrict the projection to these families. Okay. So in this case, we are going to be able to prove it's surjective. And the idea is, okay, as before, these spaces are Banach, and the projection is Fredholm of 0. And now we can prove it's proper. Why? Because you take a sequence of annuli in your family in such a way that the boundaries are converging in the family of the boundary curves. Okay, case 3 can happen because the distance of the limit is going to be smaller than pi, as I said before. Case 2 is not possible because case 2 was when the cylinders were going to infinity, but they are, they are not symmetric, so this case can't happen. So you are only in case 1, and in case 1 you had a limit. So at the end we can prove it exists a limit. And now, since it's proper, now we can define the degree of this projection. Okay, as is written there. Okay, so the index is the one defined by Joris yesterday. And okay, in the definition, this is gamma is any regular value. It doesn't depend on the choice of the regular value. So what we have to prove in order to finish is 2 things. First, that there's at least one regular value in such a way that you have something in the pre-image by the projection, because otherwise you have nothing to add there. Okay, it makes no sense. And once you have that, you have to look for some other value in order to say that this degree is different from 0. If this is different from 0, it's always different from 0. So for any regular value, you are going to have something different from 0, which means that you are adding something, so you have something in the pre-image. And now, using that they are dense by the Sartre theorem is proper, you can finally conclude that for any boundary curves, you have something in the pre-image. This means that it's proper, it's surjective, as we want to prove. Well, so first, let's prove that there's some regular value in such a way that the pre-image is non-empty. Okay, take the catenoid we fixed at the beginning. Since you are killing all the decaying Jacobi functions, what you are saying is that it's non-degenerate. So you can use the implicit function theorem, and that says that a neighborhood of the catenoid maps diffeomorphically to a neighborhood of the boundary curves. Okay, and since the regular values are dense, there are at least one in this neighborhood, and now we know that there are some pre-image. Okay, that's the simplest case. And the second thing is take this catenoid, and we know that any annulus projecting to this boundary of the catenoid is going to be a catenoid. And since we are assuming the examples are symmetric, you only have one. So you only have one annulus projecting to this boundary. If you only have one, this number could be either 1 or minus 1, but it's not going to be 0, and you're done. Okay? It's quite standard, this argument. So, as I said before, we have some other results proving existence, but we don't know which are the sharp conditions. So this is an open problem. And if there are some ideas in the audience, please let me know, because I would like to say if there exists a solution if and only if something. Okay. Now we know that there are some cases where there are no solution, some cases where they are. So we have some things stronger than the others, but we don't conclude the general problem. Okay. Well, and so we didn't like that. We tried to look for some more general result. Okay, we are not able to fix both boundary curves, But by deforming the problem, as I'm going to explain, what we are able to say is that if you give me two Jordan curves projecting graphically, we are going to construct an annulus whose boundary downstairs is the fixed one, and the second one upstairs is going to be a deformation of the one you gave to me. Okay, at least it's better than nothing. So since you are deforming the end upstairs, maybe you are going to lose embedded. Okay, so we consider, instead of properly embedded, we consider proper Alexandrov embedded annuli, but with embedded ends. We keep it. Okay, and we need a technical extra hypothesis here. That what means is that we are going to fix one of the boundary at infinity downstairs. So what that says is that, okay, we know that this Jordan curve spans an entire graph. Is the boundary at infinity of an entire graph. What I'm saying there is that this entire graph is a barrier from below of your end, of a neighborhood of the end. Okay, this is what means, which is quite natural. Okay, so the projection is going to be different. Okay, we are fixing the boundary downstairs, but we are deforming the boundary upstairs. We are adding some constant, which means we are allowing some vertical translations. And this second part means that you are allowing some tilt. Okay? But okay, doing that increases the domain of definition. Okay? So in order to, this is finite dimensional, it's not going to be a problem to say that the projection is Frehon. Okay? But in order to keep index 0, we need to add the same dimension in the rank. Okay, so we add that, and we are going to add two things. But to be honest, it's the opposite. Okay, so these two things, I'm going to explain what they are. What is avoiding is to have case 2, which was bad, and case 3. Okay, so we were forced to add these things, and in order to keep the dimension, we allowed to perturb the boundary upstairs. Okay, that's the thing. Okay, now I'm going to explain what they are, these new factors of the projection. The first one gives you information about the flux. Okay, this is the flux of your annulus. Okay, and we observe that that if the flux is going to either 0 or plus infinity in a sequence, what is happening is that this number here is going to infinity. Okay, so in order to prove that this projection is proper, if these numbers here in the sequence convert, what we are saying is that the flux is not going to either 0, you don't have a pinching, nor infinity. It doesn't, the case 3 is not happening. In order to prove that case 3 doesn't happen, we need this technical condition I said before. Okay, but it's natural. The second factor there is what we call the center of the annulus. Why? Because, okay, if you forget this part now and this part, what you get, if you do that, is the flux. Because since this is V was defining the graph, the contribution there is going to be 0, so you have the graph. Okay? So now we multiply by the exponential, and the idea is that we want to have something bounded whose modulus is 1 in order to say it's a point in the unitary disk. So we divide by the flux there. Doing that, you can compute that this is in fact is a complex number, but the modulus is less than 1. So what is given to you is some point in the hyperbolic plane. Okay? And moreover, you have a point in the hyperbolic plane. And also we can compute explicitly what is that for the catenoid and is the center of the catenoid. And also we can prove that in the case you have a sequence, and in the case that these numbers here associated to your annuli convert, what means is that the next are not going to infinity. That means that the centers of your annuli remain bounded. This is why we call it the center of the annulus. Okay. And what we prove here is that, okay, as I said before, I already said that this projection, this new projection, is Fredholm of index 0. Okay, we know that. And also, because we are avoiding case 3 by adding this term, and we are avoiding case 2 by this new term there, what we prove is that this projection is proper. Okay, so we can follow exactly the same proof as before, and what we get is that this is a proper Fredholm map of index 0, and the degree is non-zero. In order to do that, we need uniqueness for the catenoid, but we can prove that. Okay. So at the end, what we prove is that the projection is surjective when restricting the rank to D instead of C here. Okay. Because we need some point in the hyperbolic plane. And in particular, what we are saying is that it exists for any two Jordan curves graphically projecting to S1. You have a minimal surface whose boundary downstairs is the fixed one, and the second one is maybe a deformation of the previous one. But we are saying something more. We are saying that also we can prescribe. I mean, we are losing information in the second component, but we can fix both the flux of your annulus and the center of the annulus. So at least there's an equilibrium there. Okay, I think I can stop here. Thank you very much.